Welcome to today's explainer. Step right up to our interactive chalkboard. Today, we are going to completely demystify the physical forces and the mathematical rules that govern the beautifully spinning world all around us. From the wheels on your bike to a spinning compact disc, we are going to uncover the hidden mechanics of spin. Here's our roadmap for this explainer. First, the language of rotation. Second, 3 types of acceleration. Third, the kinematic mirror. Fourth, moment of inertia. Fifth, the parallel axis theorem. And finally, energy and momentum. We're going to build these concepts up logically, step by step, so no one gets lost in the math.
All right, kicking things off with Section 1, the language of rotation.
Before we can really deconstruct a spin, we've got to learn its native language, and that is the radian. Now, you're probably used to thinking in terms of degrees, right? 360 degrees in a circle. But honestly, in physics, degrees are completely arbitrary. Why 360? It's just a historical convention. The radian, though, that is the natural, fundamental bridge between linear and rotational geometry. Picture taking the radius of a circle and physically laying that exact length along the curved outer edge. That angle you just created, that is exactly 1 radian. Because of this direct, pure relationship, formulas relating arc length, radius, and velocity work flawlessly. So for this explainer, we're tossing out arbitrary degrees entirely.
Moving right along to Section 2, 3 types of acceleration. So there's a sort of tale of 3 accelerations that dictates exactly how an object moves in a circle. Let's group them together using the rule of 3. We've got angular acceleration, tangential acceleration, and centripetal acceleration. Now, we absolutely have to point out a crucial distinction here. That first one, angular acceleration, represented by the Greek letter alpha, is an angular quantity applied to the entire rigid object as a whole. Think of a spinning CD. The whole thing has 1 angular acceleration. But those other 2? They are linear quantities, meaning they depend entirely on exactly how far out from the center you're measuring. Let's draw a really sharp contrast between those 2 linear quantities on the edge. Tangential acceleration, that's what changes the actual speed or magnitude of the object moving along the edge. Like if you hit the gas pedal while driving in a circle. Bam, that's tangential acceleration. But centripetal acceleration is a whole different ballgame. The word literally translates to center seeking. It doesn't speed you up or slow you down. It constantly changes your direction so you actually stay on that circular path. And here is the dramatic truth of physics. Without that center-seeking centripetal acceleration, circular motion is literally physically impossible. The exact millisecond it drops to 0, boom, you're flying off in a straight line. Now, what's really interesting is how we visualize angular acceleration for the whole object. We use something called the right-hand rule. Basically, angular acceleration depends on the change in angular velocity over time. So, if the spin is speeding up counterclockwise, you literally just curl the fingers of your right hand in the direction of that spin and stick your thumb out. Your thumb points straight up along the axis of rotation. And it's that invisible axis that governs the spin direction for the entire rigid body. Okay, let's jump into Section 3, the kinematic mirror. Think of this as our Rosetta Stone. We act as a translator, mapping the linear motion concepts you already know directly onto their spinning counterparts. Think about the relationships here. Displacement, s, becomes angular displacement, theta. Velocity, v, becomes angular velocity, omega. Acceleration, a, becomes angular acceleration, alpha. And if you think about the relationship between them, the pattern is always exactly the same. The linear quantity equals the radius multiplied by the angular quantity. So the radius is acting as this perfect mathematical bridge connecting the straight line world to the spinning world. Oh, and mass, which is a measure of linear inertia, translates perfectly to I, which is the moment of inertia.
Which brings us perfectly to Section 4, moment of inertia.
So now we're shifting our focus from the motion itself over to the physical resistance against that motion. Just like mass resists being pushed in a straight line, moment of inertia resists being spun. But first, we need to differentiate the types of axes we're dealing with. Think about a bicycle wheel rolling down the street. That's a translating axis of rotation. The wheel is spinning, sure, but its center of mass is also physically moving horizontally through space. Now compare that to a spinning CD. That is fixed axis rotation. The axis stays perfectly locked in place while the rigid body spins around it. Both experience moment of inertia, but fixed axis rotation is the absolute purest way to study it. So I'm going to pose a quick Socratic question directly to you, just to get those cognitive gears turning. Imagine you have a few different objects, and they all have the exact same total mass. Which one will have the largest moment of inertia? Meaning, which one will be the hardest to get spinning?
Take a second and think about it.
Okay, let's dive into this. The secret is that moment of inertia isn't just about total mass. It's fundamentally about how that mass is distributed away from the center of rotation. Take a hollow cylinder, a solid cylinder, and a thin-walled hollow cylinder. Because that thin-walled cylinder pushes almost all of its mass way out to the very edge, the absolute maximum distance from the central axis, it is going to have the highest moment of inertia. It will stubbornly resist spinning up way more than the solid cylinder, even if they weigh the exact same amount on a scale. Now, for continuous, solid objects with complex mass distributions, we can't just guess. And that brings us to the actual physical reality of the integral formula for moment of inertia, which is I equals the integral of r squared dm. And hey, don't let the calculus intimidate you here. It literally just means we're summing up an infinite number of tiny, microscopic pieces of mass, that's the dm part, and multiplying each of those tiny pieces by its square distance from the axis of rotation, r. You add the whole shebang together, and you get the total resistance to rotational change.
All right, moving to section 5, the parallel axis theorem. So what happens mathematically when our spinning anchor object doesn't rotate perfectly through its natural center of mass? Imagine a sort of potato-shaped rigid body. Suppose we want to spin this thing around a totally new parallel axis, rather than its perfectly balanced center of mass. Well, the parallel axis theorem handles this beautifully. To find the new moment of inertia, you simply take the original moment of inertia through the center of mass, and then you add the total mass of the object multiplied by the square distance between the two parallel axes. It is just a brilliant, incredibly simple mathematical correction that lets us spin an object around literally any point we want.
And finally, section 6, energy and momentum. Let's bring this whole translation exercise full circle and apply these new angular terms to our fundamental conservation laws. Just as a swinging pendulum or a sliding block conserves linear mechanical energy, spinning objects conserve rotational energy in fixed-axis systems. Translational kinetic energy is 1/2 mv squared, and rotational kinetic energy, it's 1/2 I omega squared. And this brilliantly illustrates how flawlessly our Rosetta Stone translation works. We literally just swapped out mass for moment of inertia and linear velocity for angular velocity. The underlying physics doesn't change one bit, just the geometry of the movement. The exact same thing happens with momentum. Just as a heavy sliding block has massive linear momentum, where P equals mass times velocity, this translates perfectly to angular momentum, where L equals I times omega. It means that understanding the complex momentum of a spinning baton tossed in the air, or a CD spinning up in a drive, is now as simple as just plugging in the angular cousins of our familiar linear equations. As we wrap up today's explainer, I want to leave you with one final provocative thought. If circular motion is truly physically impossible without centripetal acceleration constantly yanking an object inward, what actually happens to a spinning object the exact millisecond that center-seeking force suddenly vanishes? I'll let you ponder the fragile, mathematically precise physics of the spinning world around you. Thanks so much for joining me for this explainer, and keep questioning the mechanics of your world.